Hi everyone, it's Mr. H here. In this video we're going to look at the Pulley problem. The Pulley problem is a classic problem in physics, and it's something that was actually on the grade 11 physics exam. So that's the question I've pulled off of one from the previous physics exam. And it says this: a 10 kilogram block M1 is attached by a massless string to a 3.50 kilogram hanging mass M2 as shown below, shown on the right. An object is placed on block 1 that exerts an extra 15 newtons downward force on block 1. Block 1 then begins sliding as block 2 begins to fall. The coefficient of kinetic friction between block 1 and the table is 0.284. Part A asks us to find the acceleration of the two blocks. Assume there's no air resistance or stretching of the string. Include free body diagrams. And part B is determine the magnitude of tension in the rope. Now this is a pretty classic question. The only wrinkle that we've thrown in here is that we have this extra 15 newtons downward force on block 1. And so just before we draw the free body diagrams, it's worth just discussing and thinking this through. If I have that extra force, there's a couple of ways I could put that force in play. One is I could put some mass on top of this, or the other thing I could do is I could push down on it. Now here it says an object is placed there, so we have to assume that that mass is being put on top of it. However, if I push down on it, is that any different? Well, let's think about this for a minute. If you, and probably this is the easiest way to think about it, if you were standing beside M1 and you put both of your hands onto mass 1 and you began pushing down, that is a force that you're an applied force that you're pushing downwards on it. But then how would that change if your entire body went up on those two hands on top of M1? Well, at that point you are part of that mass M1. So really the difference between pushing on something, exerting an applied force, and affecting the force of gravity, they're the same thing. Now, keep in mind here that whether or not you call that an applied extra force or you call it a force, you include it in the force of gravity, you can do either one of those. I'm going to include it in my force of gravity because we're told that the object is placed on top of it. So therefore, we have to interpret that 15 newtons as a mass. So we need to determine what the mass is for that 15 newtons. And that's going to incorporate for our M1. So let's go ahead and let's draw the free body diagrams. So here's the first free body diagram. So this one is FG2. I say it's the first free body diagram, but remember this is M2 over here and M1. So I'm just going to draw them in the order that they are in the picture. Then we're going to have a force of tension of 2 on 1, or rather this would be 1 on 2. This force of tension is 1 on 2. And this force of gravity, just to be very clear about this, it should be larger than the force of tension because it's going to accelerate in this direction. So we're also going to, on our diagram, label those as the positive direction. And so that's going in a positive direction and downwards. So that is mass 2. For mass 1, the mass that's sitting on top of the flat surface, that's going to look a little bit more complicated. We're going to have this force of gravity that's acting downwards. We're going to have this normal force that's going to be equal and opposite. Now keep in mind this includes the 15.0 newtons. We're also going to have a kinetic force of friction that's going to try to oppose the motion. And a slightly larger force is going to be the tension of 1 on 2. That's what's actually going to cause this whole thing to accelerate. And in this direction, or in this free body diagram, that is again the positive direction because it's going to accelerate to the left. I'm just going to label that those are equal and opposite. So that's our free body diagrams, but for these types of problems, we want to draw a system free body diagram. That is always going to simplify it because what it does is it eliminates for us that middle force of tension. And we can come back to one of the other free body diagrams to answer part B. So here we go. Our system free body diagram is going to look like this. We're going to have a force of kinetic friction acting to oppose the motion. So I'm going to say this way is positive and forwards. We're going to have a normal force that acts on block 1, and it acts on, I'll label that there, FN1, and it acts on the mass that's put on top of block 1. We're going to have a force of gravity acting on block 1. These are, as we said, equal and opposite. And then we're going to have this force of gravity of block 2. That's going to accelerate the entire system forwards. So now that we have that system free body diagram, that is what we're going to use to simplify our life. If we didn't have the system free body diagram, we'd actually have to create from Newton's second law two systems, or two equations, and we'd then have to find, we wouldn't know acceleration and we wouldn't know the tension force, so we'd have to use substitution or elimination to solve two equations with two unknowns. With the system free body diagram, we're going to get one equation and we're able to solve force of, or the acceleration directly. So here we go. The net force is equal to the total mass times acceleration. Now be careful here. What's the total mass? Well, let's take that 15 newtons mass and let's see what that becomes. So we know that force of gravity is mass times acceleration due to gravity in general. And for the 15 newtons force, we need to determine what that mass actually is. So what we're going to do is we're going to divide both sides by g, because we know what g is. And so the force of gravity in this particular case was 15 newtons. G is 9.8 meters per second squared, or newtons per kilogram. And so we're able to solve the mass here. So the mass of this particular object is 1.5306 kilograms. Now I've kept extra significant digits because we always keep at least two extra significant digits until the end. So what's the total mass? Well, the total mass then is going to equal mass 2 plus mass 1. Well, mass 1 is, mass 2, let's just be clear here first, is 3.50 kilograms. That was the hanging mass. Mass 1 is 10 kilograms plus this extra 1.5306 kilograms. That gives me a total mass of 15.0306 kilograms. So that's the total mass that I need to use for this equation. Well, let's break down the net force. The net force is the force of gravity 2 on acting on the hanging mass, plus the force of kinetic friction. Total mass, and we can just say mt for total, times acceleration. So accelerations ultimately we need to find. Let's break down the force of gravity and Fk. We know the force of gravity is in the positive direction, so it's going to be a positive. So we're going to drop the vector sign and just say it's m2 times g. And we know that the kinetic force of friction is in the negative direction, so we're going to subtract that. We're going to drop the vector sign there, and this is going to be mu k Fn. So now the only place we have a vector is on the acceleration, and it's because we've taken the directions into account by the signs on both the force of gravity and the force of kinetic friction. So now what I need to do is figure out just a few more things here. I know what m2 is, I know what g is. I don't know yet what Fn is, but I do know that Fn is Fg1. So since no acceleration up or down on that second mass, that means that Fn must be equal in magnitude to Fg1. So we can say that because Fg1 is equal, that means that it's m1 times g. Now keep in mind that that m1 is now 10 kilograms plus 1.5306 kilograms, because we've added to that total mass. If we keep going with this, what we get is just dividing both sides by the total mass, and we arrive at this. So subbing those values in, we get an answer, and I'll do that and show the answer to that. So what I get are those values I substitute in, and what that leads to, some of you might have calculated it separately, it leads to negative 32.092 newtons for the force of kinetic friction. And overall, it leads to an answer of 0.1469 meters per second squared. Now, I've kept a couple extra sig digs because I'm going to need those for the second part of the question. But this particular answer to two significant digits, because the acceleration due to gravity is only 2 sig digs, we would say, therefore, the acceleration of the system is 0.15 meters per second squared forwards. 2 significant digits. So let's just finish up by answering the second part of this. So that brings us to asking about the magnitude of the force of tension. So what is the magnitude of the force of tension? Well, the easiest way to solve that is the easiest free body diagram. We have to use one of the two original ones, not the system free body diagram, since the force of tension is an internal force. So we're going to use this second mass's free body diagram. So we set up Newton's second law, and because it's mass 2, we don't use the total mass here, we use mass 2. The net force is made up of the tension of 1 on 2, and it's made up of the force of gravity on 2. Now we know everything but the force of tension, because we know that the force of gravity is m2 times g. And because that is positive, we can go ahead, it's in the positive direction. So I'm just going to get rid of the vector sign and make it a positive number. And I'm going to rearrange this to solve for the force of tension. m2a minus m2g. If I can get that to write properly, there we go. All right, let's just scroll down a little further and continue to solve this here. So this is going to give me the mass 2 is 3.50 kilograms. My acceleration was positive in forwards, 0.1469 meters per second squared. Now notice I'm putting those 2 extra sig digs there. From that, I'm going to subtract the mass 2 again, which is 3.50 kilograms, times 9.8 newtons per kilogram, or meters per second squared. And I get a total answer of negative 33.79 newtons. Now, obviously in this particular free body diagram, that's a negative force because it's acting in the opposite direction of the acceleration. But in the mass 1 free body diagram, that's a positive force. And so those are internal forces. One is positive 33.79, one's negative 33.79. They're going to cancel each other out. So that's why the question just says the magnitude is what we're concerned about. Determine the magnitude of the tension. So let's answer that with our therefore statement. Therefore, the magnitude of the force of tension is 34 newtons, 2 significant digits. So there's your final answer, and hopefully that's helpful. I would just write that down, make sure you have a good grasp on that as we go into the next one where we're going to add a slant to this whole problem.